Now that we have set up the idea of electric potential, we want to apply it to something other than in a uniform field. We've already discussed the electric field around a point charge, and we know that it is anything but uniform. We have the field radiating out from the point in all directions, but as we get further away from the point charge, the field gets weaker. So describing the strength and direction of the field depends on where you happen to be within the field. If we take the connection between work and potential, we can do some calculus and determine the electric potential of a point charge. But you know what we're not going to do? Calculus. This particular derivative requires quite a bit more in terms of math than this course requires. So for our purposes, we are just going to define the electric potential of a point charge as a constant k times the magnitude of the point charge divided by the distance away from the point charge. In this case, the constant is 9 times 10 to the 9th Newton meters squared per Coulomb squared. So now we are no longer looking at the change in potential from one point to another, but the potential at one point. Now here's what's interesting. This is not a vector quantity. So if you have more than one point charge within your field, all you have to do is add up the individual voltages. The electric potential will then be the sum of all of the point charges. Now if one of those charges is negative, it will reduce the amount of electrical potential. So what is the voltage 5 centimeters away from the center of a 1 centimeter diameter metal sphere that has a negative 3 nanocoulomb static charge? We are looking for the voltage and we know the charge on the particle and the distance from the sphere, so this nicely fits into our equation. Nano, remember, is 10 to the negative 9th, and since it is 10 to the negative 2nd, and we find a negative 540 volts. Suppose a Van de Graaff generator has 25 centimeter metal sphere that produces 100 kilovolts near its surface. What excess charge resides on the sphere? In this case, we are looking for the charge and we know the voltage and diameter of the sphere. Kilo means 1,000, so we actually have 100,000 volts being produced. The surface of the sphere is half the diameter, or the radius of the sphere, and we end up with 1.39 microcoulombs of charge.